Hello everyone, my name is Xiang. The title of our paper is Overcoming Catastrophic Forgetting for Multi-Label Class-Incremental Learning. I will introduce it from the following three aspects: introduction, methodology, and experimental results. The first is the problem with current incremental learning. Existing CIL methods only focus on single-label classification. However, in real-world scenarios, multi-label images containing multiple objects are more common. These CIL methods ignore the more general multi-label CIL task. From the figure on the right, we can see that the CIL above only needs to learn new classes in each session. The MLCIL below requires the model to not only classify new categories on a single image, but also to classify previously learned old categories. One way to address MLCIL is to migrate current CIL methods directly into a multi-label setup, but this approach brings several new challenges, like the label absence problem, the representative sample selection problem, and the feature dilution problem. Furthermore, another feasible approach is to implement class-incremental object detection, or semantic segmentation methods in MLCIL. However, they require bounding box information, or pixel-level mask annotation, which significantly increases labor costs. In contrast, the labels for multi-label classification are simple. Only the object category information in the image is required. Therefore, we propose the Apple framework to solve the MLCIL problem. The figure on the right shows our proposed Apple framework. It contains three parts, namely adaptive pseudo-label strategy, cluster sampling strategy, and the class attention decoder module. In session T-1, we use the CS to select the representative samples as replay data. Then when training in session T, we freeze the old model to generate pseudo-labels by a PL for new model training. The learnable class tokens are fed into the CAD along with the backbone output to better focus on spatial information, thereby alleviating the object feature dilution problem. First, I introduced the adaptive pseudo-label strategy. We propose to utilize an adaptive threshold to determine the value of the pseudo-label. We can assume the proportion of the same category objects in different sessions is the same. Given the average number of K-class objects per image in session T-1, we can adjust the threshold according to this relationship. Then the clustering sampling strategy. The size of the output feature is K times D. K is the number of categories and is the embedding dimension. For KTH class, the output feature is K times 1, so we can get the feature set F. We divide the feature set into different clusters by the k-means clustering method, thereby selecting samples with large intraclass differences. Then the CAD module. CAD is composed of LN, MLCIL, and MLP. Using CAD, the problem of object feature dilution is well alleviated. For the overall objective, following the recent progress, we adopt the knowledge distillation loss to overcome catastrophic forgetting and use a SL to address the positive-negative sample imbalance problem. Table 1 summarizes the last and average results of ResNet 101 and T-ResNet L backbone under the B40C10 and B0C20 protocols on the MS-COCO dataset. For the B40C10 protocol, Apple with the ResNet 101 backbone achieves the highest last and average accuracy. For the T-ResNet L backbone, Apple outperforms the second best TPCIL by 3.41% for the last accuracy, and 6.77% for the average accuracy. For the B0C20 protocol, Apple also exceeds the other methods. Table 2 summarizes the results under the B10C5 and B0C5 protocols on the PASCAL VOC 2007 dataset. These results have similar trends to those on MS-COCO. Table 3 demonstrates the ablation experiments under the B40C10 protocol on MS-COCO dataset. Model 1 is simply fine-tuned as a baseline. In Model 2, the CAD is added, getting a 6.01% relative improvement of the last accuracy. Then, in Model 3, we further add the K, D, and CS, boosting the final accuracy by 37.52%. In Model 6, we add the APL to Model 3, resulting in a 9.97% improvement. Model 6 is the Apple framework we proposed. For comparison, we replace KD, CS, and a PL in Model 6 with KD, HS, and FPL, obtaining Model 4 and Model 5, respectively. Their final accuracies are both lower than ours. These results above strongly prove that our proposed 3 components are very effective in improving performance in the MLCIL setting.